you will be able to understand these problems once we go through the building blocks. But just wanted to put it out there that eventually, after today's class, you will be able to solve these problems. These are really easy problems. Looks complicated, but it's not. Okay, so first we'll go over the basics, and then we'll come back to these questions. So in our quiz, we did actually convert the MIPS instructions to binary, right? So we know that this is an opcode, RS, RT, RD, like those registers, and then you have a function. The function tells us whether we are doing an addition or a subtraction, XOR, or like, and in our previous lectures, we have also gone over some of the circuits that we need, like ALUs, decoders, multiplexers. So all that will come into play, and we will see how an instruction gets executed inside, like at a hardware level. So before we start, we know that we have three types of instructions: R format, I format, and J format. And the aim of today's lecture is you will be able to understand from, like, you get the current instruction from the program counter, which is PC here, right? And then how it goes into the register file, how it gets executed. So at the beginning of the class, I show you, like, we will use this same processor again and again, and you will be able to trace how an input goes and how do we get an output after running an instruction. So in the exam, you will be given this blank processor, right? Picture of this blank processor, and then you can, maybe it's better to use a color pencil, or I'll make it ash, ash color, so that you can just do it with your black pen. So you can complete the question. Okay, so two really good tutorials you can follow. Let's jump straight to the different components. So you see that we have we have a memory here and a memory here, right? We have the register file. So the register file has this red one is the register file, has the 32 registers in MIPS. The program counter PC has the next, like the current or the next instruction. Every time you do an instruction, you fetch it from the program counter. So it points to the current instruction, and then you move to the next instruction, and so on. The ALU is the ALU is the component that does all the mathematical and the logical operations, like you do add, subtract, you can do an OR, AND operation, right? So we do those things. Remember, for branching, we sometimes have to shift bits. So we do need that option to shift 2 bits. Also, remember, for I-type instructions, the immediate value is 16-bit, right? But the ALU only handles 32-bit, like 32-bit addition or operation. So then we have to sign extend that 16-bit to make it 32. So these are the key components. And what you see in the bottom is like sequential and combinational, which are which operations. We left that for later because I thought this topic should be covered well before the final, so that because this carries a lot of weight in the final. So we will go over combinational and sequential circuits, but I wanted to cover this topic first. Okay. So now that we know the different, what are the different components in this figure, let us look at an individual level, what happens. Basically, you have three major actions when you execute an instruction. You first have to get the instruction, right? You have to fetch it, get the instruction from memory. You have to know what's the next instruction, right? So when you get the instruction from memory, the next instruction is likely to be +4 of that, unless you do a jump or a branch. So in the fetch stage, you get the current instruction. Now, once you have the instruction, you decode it. So by decoding, you tell the ALU what operation it needs to do. Or if it's a jump instruction, you don't use the ALU, you directly jump to the address, right? So by decoding the instruction, we know what to do. And once you know what to do, you execute. So if it's a add or a for branching, you need to use the ALU to get to, the offset. You have to add the offset and then go to the designated location. So for branching, you need to use the ALU, but you don't need to use the ALU if you are doing a jump operation. So we'll look at each operation one by one. So the most easy to understand is this getting the next instruction. So you get the current instruction here from the program counter, and this is the current instruction, and you add 4 to get the next instruction. And now PC, once you have once you have fetched the current instruction, you can now set PC equals to next instruction. So that's what it's shown here. Okay, this is what happens for fetching. You get the current instruction and you make the hardware ready for the next instruction. So now for decoding, you can have three different types of instructions, right? R type, I type, and J type. So if we consider the most basic one, which is the R type, you have 32-bit instruction, right? And you know that the first 6-bit is the opcode. So the opcode goes to the ALU control to let it know that we have to do this operation, right? So the opcode goes here, and you have RS, RT, RD, right? So RS, RT, and RD. RD is here. These are five bits, right? Can anyone say why is RS, RT, and RD 5 bits? Anyone can answer why is RS, RT? Yes. Yes, because no. We have 32 registers, right? And this register file, it's actually a decoder. So you give it a 5 input and you get like you select one of the 32 options. So so with 1, 2, 3, 4, 5, with 5 bits, you can at max point at 32 items. So if you have RS is 5 bits. So RS will point at one of those 32 registers. That's why this register file works as a decoder, right? And RS selects a 32-bit value here. Like RS selects a register, and we know in MIPS, each register is 32-bit, right? Each register holds 32 bit of data. That's why when you have RS, it's pointing at one of the 32 registers, and that register will have a 32-bit value inside it. And once you have RSRT, you can put it inside the ALU, right? And if it's the add operation, then the ALU will do the add operation, and it will put it back to RD. It will put it back to RD if your R-type operation writes back to the register file. RD is the destination, but in some, remember, in some R-types, you don't write back to RD, right? So in that case, we wouldn't need it. But basically, to sum it up, the decoding, what happens is you have a 32-bit instruction, and it separates it to, okay, what registers do we need to select? What's the command? That's basically decoding. Do I need to do an add operation? Which 2 registers do I add up? That's the what we do with decoding. Okay. Any questions? Yes. Oh, yes. Now, like it goes in. So as I said, I have a eraser here. So as you can see, with this RSRT, right, we select registers. But you can see for the jump, we don't have any RSRT, right? So it just goes to the control signals and tells it, we don't need to use any registers, just jump to that location. Yeah. So, and for I format, we do not have any RD, right? So it says it's going to be either a memory operation where we don't manipulate the register file. We can manipulate the memory, but we won't, there's no RD. So we won't manipulate this register file. We can take values from the register file. It will read from the register file, but it won't write back to the register file for I type using the RD. It uses the RT for the load operation, right? So load from memory and store to memory. So we will look at it one by one, but basically what I'm trying to say is basically decoding is you have a 32-bit instruction and you divide it like this and put it into different, so if it's the opcode, it goes into the control and says, okay, for this opcode, we have to do this operation. Basically, decode does that, tells you what to do. Now, for execute, we perform an action, right? So if it's an addition, we select RS here, RT here, right? And RD here. So now this is RS, this is 5 bits, right? But 5 bits selects a 32-bit value. This is like the RS, the 32 value the RS selects. This is the 32-bit value RT selects, right? And then because this is an add operation, we send a signal to the control telling it it's an add operation based on the opcode and the function. And it gets the result, which is RS plus RT, but not the registers, but the values, like the 32 value stored in the RS register and 32 value stored in the RT register. And it gets a 32-bit output, which gets stored back to RD. And using RD, you select which register you manipulate at the end. Yes. Yes, it's like you have register 0. It has 32-bit, like it has a value. And you have register 1, ... register 31. And it has a value. And basically, RS, RT, RD are selectors. I select this register, and maybe I'll select register 15. And then if I set RD as, let's say 10, I add these two values, and the result gets stored in RD, which is register. So yes, it's like, your processor, you have your processor, right? Intel or AMD. So inside your processor, you have registers, more than 32. We are studying 32 because it's simplistic. We can understand 32, right? But registers are really costly. So but registers are very fast. So if you do an operation, you want it to be executed fast, right? So you use one of the registers inside the processor, and you keep the values that you most use in those registers. But sometimes you have your RAM, right? Sometimes you are using an infrequent value that you don't use frequently. You then have to get it from memory for store and load. But inside the registers, like inside the processor, you have the register file. You store the most used numbers there. So, and optimize, keep what values you need. You need to like add multiple times, multiply. So, and then you select two of the registers, right? And then you add it or subtract it, and you save it back in an R-type instruction. But does that answer your question? So that will, the operating system will determine that. We have like different algorithms to, okay, we need to store like this. Let's say you have the Chrome browser open, right? and you have other things on the background. So your computer now knows that you have it on screen. So let's keep the things that are related to the Chrome browser in the processor, and the other things we can keep it in RAM, you know, and the most important things, the most important values, because everything is zeros and ones inside the computer. So it has like algorithms to choose, I should keep these, you know, but we can chat about it later because we'll go out of topic. But it's really nice that you are thinking about why we are doing it. Yeah. Okay. So for the store word, what do? We add these two to get the address, right? Address, RS. So RS and this, so this is the offset going here, the 16-bit offset here, right? And we have RS, so RS going here. So RS goes here, and then the offset goes here. We don't use RT inside the ALU this time because we now need to RS plus offset, right? And then we get the memory location. The memory location where we will store the value of RT. So RT stores the value in that calculated location. This is how the store word works. Any question on this? Because we know how a store word works, but we haven't seen a circuit diagram how it works. RS and RT and this offset, these are fed into the ALU, and the RT directly goes into the memory based on which location this selects. Any question on this? Okay. So moving on to the next step. But, you know, what load word does is the exact opposite. So load word with RS and the offset, you select which location from the memory. For memory, we normally call RAM as the memory. So we select a location in memory, and all of the values in MIPS is 32-bit. So every location holds a 32-bit value. So that 32-bit value gets stored into RT. So this value gets, like, we manipulate the register file, we replace it with a value from the memory using the load word. We'll again go over this, but I'm just, any question on this? Basically, you're loading from memory, right? From memory, you are this part. So this is the memory. You're loading from the memory to the register file. That's what load word does. But which memory value? That gets selected by RS and the offset. So you get the offset here. So, but the offset is 16-bit, right? The ALU can't work with a 16-bit value. So you just sign extend the 16-bit value, make it 32, right? So just add zeros to it in most cases, because well, for branch you can have negative values, right? So you can have, you just sign extended if it's negative or positive. You just know, yeah, just do the, put in the offset and you get the location. From that location, you get the value and put it into RT. Basically, you are just putting this value into RT. Any question on this? It might look a bit confusing at the beginning, but these resources that are here, like the videos, they also explain it in a similar way or better way. So you can like go through it, go through the lecture, and if you practice it, there are some practices. So if you practice it, you'll be good. And I won't test you anything other than we covered, you know, like maybe, so if I teach you add, branch, store, load, and jump, right? I'm not giving you a question on SLT. So don't need to worry about it. Just you need to practice it. Okay. Now, these are, we have drawn different diagrams for different operations, right? But we need one hardware that does it all. So that hardware looks like this. And we achieve that by having different control signals. So you remember with a multiplexer, you can choose between two options. So you need a control signal that says the register will be overwritten, 0 or 1. If it's 1, yes, it will be overwritten. But if it's 0, no, there is no register overwrite. Is the memory going to be overwritten, or am I going to read from the memory? But you know, for R-type instructions, you do neither. So these control signals, they help you make choices where you have one circuit, and with one circuit you can do all of these operations. So if I just recap that, we need to use RD if there's a register overwrite. If we are doing a store word, then we need to store the ALU result into memory. But if we are doing a load word, then we need to load from memory to register. So that's why if we combine all of the individual components that we learned, if we combine them, then we have one circuit that does them all together. Any question on this? I can show you some quick things. This register destination, right? This basically can be 0, 1. 1 means we will use RD. 0 means we won't use RD. So that's one thing. This mem write. If mem write is 1, we will write to memory using this line. But if memwrite is 0, we won't use this line to write to memory. If we are reading from the memory, we still have to make the choice whether we are writing back to the register or not. So is mem register, if it's 1, we are writing back to the register file from memory. But if it's 0, we are not writing back to the register file. So basically, using multiplexers, we are making decisions which line we are going to go through. And it will all be clear when we go back to the questions we, like when we do this, right? Then you'll see, okay, this is an add operation. So I don't need to use the jump. So whatever is blue, I don't use it. Whatever is red, I use it from these diagrams, right? So when we come back to this, after going through the individual components, it will make sense. The red ones are the ones which are being used, and the blue ones are not being used. And it depends on the instruction. So we were here. Okay, so here are some practice problems, you know. So we have some in the exam, right? If you have this 9, 10, right? And it says 9, the register 9 holds a value of 13 and register 10 holds a value of 25, right? Then how would it look for the add operation? So how it would look like the register number 9, the value 9 goes into this and the value 10 goes into this. And because we know what's the value that register 9 holds, we can have this 32-bit value, which is 13, and this 32-bit value, which is 25. And then we know the result will not get added to memory, will not get replaced in memory, but it will be replaced in RD, right? So we will not manipulate the memory, but it will follow this path and it's going to be a write back to the register. So in your exam, I can do it for only data path, right? Because see here, I'm not like, you can, there's 2 components here. One is how the data is flowing, and the other is what's the control values. So if I zoom in, so see here, the opcode determines the control signals, right? I can give a broader question where I tell you to decode the what am I getting out of the control and what is the data path, or I can separate the question. Just tell me what will be the control signals, or just tell me what will be the data path, you know? So this answer has both the control signals and the data path. We'll come back to this practice because we have some practice above. We'll come back to that. But basically, this is a question that you can have. If this is an operation how would you do it? So let us just quickly try. So we know that the RS, RT, okay. This is, you have the RS and then the RT. Wait. So you need to go back to the in your cheat sheet, you will have that this is RS and this is RT, right? You have that in your cheat sheet. And this is the offset, like you had it for the quiz 2. You use these information to get the binary values. And this will be similar. So you know this is RS, right? So RS goes in, and we are not going to use RT here because we're using the offset, right? So the offset goes here and gets extended to a 32-bit value, and then it goes to the ALU. Now, this is a load, so load from memory, right? So the results goes into the RAM and selects which value you are going to load. So let's say it selects this value. So this value goes here and comes back here and writes to RT. So we are going to write to RT, not RD. So we are going to write back. This selects where we write back, and this selects what value we are going to write back to the register file. And yeah, I will give you practice questions you can practice on and the solution so that you can practice these. Now, we have mostly focused on how the data moves, right? But we didn't focus on how the control signals work. So let's look at this branch instruction. For branching, we know we need to compare two things, right? Whether these are equal. If they are equal, we are going to this location, right? This offsetted location. So we do need to use the ALU to compare if $1 double equals to $2 or not, right? That's why for branch instructions, you do need to use the ALU. You get RS, RT, and you compare them, whether they are equal. If they are equal, then you select whether to branch or not. If they're not equal, you will select PC plus 4. But if they are equal, you're going to branch. Like you're going to branch off to another location. So using this multiplexer, you select whether you're choosing PC plus 4 or you're branching to a different location. But that depends on the ALU operation, whether 1 or 2 is equal or not. We're still showing the flow of the data. So which is the data path. For jumping, we don't need to use the ALU at all, right? Because we directly, this is branching isn't implemented here, but we have to go to another location. So I'm looking for, okay, this line. You see this line, 26 bits. I just need the 26 bit value, and I need to shift it by 2, and then I add the first 4 bit from PC, the existing PC, and I directly jump to this location, and I am done. The only thing that we need to do is the opcode. The opcode goes to the control and says this is a jump instruction. So only we use this and nothing else. So it just tells use that 26 bit value and don't do anything inside the ALU because it's you just need to jump. Now, as I said, we have looked at the data path, which is the flow of data. We didn't focus on the control path, but basically the control path, you don't need to memorize it. It's very intuitive. So we'll just look at how it works. So you get the opcode, right? The opcode says what to do, whether we are using the ALU or not. And if it's a R-type instruction, you have the function. The function tells you whether you need to do an add, a multiplication, a OR operation. So we use the opcode to control what we are doing in the processor. We previously saw in our previous lecture, we showed how we can build an ALU, and you did it in your quiz 2 as well, right? But we don't need to memorize these, right? Because they have been done to make it optimal, but we don't need to understand that why this value leads to this particular value. They just did some optimization and they came up with that this is the optimum. If we use these 4 controls, we can represent everything with these 4 operations. And for R-type, we can do addition, subtraction, AND operation, OR operation, and shift left than, store less than. So if it's smaller than something, store 1. Set less than. Yeah. And for load and store, you need to add the offset to the register value. So for both load and store, you perform addition or subtraction based on if the value is negative or not. For branch equal to, you do subtraction because you remember if I want to know is 5 equal to 5, what do? I subtract 5 from 5 and check if the answer is 0. So for branch equal to, branch not equal to, you just do the subtraction operation. And R-type, I-type, J-type, they give what should be done. What should the processor execute? And they have found that, as I said, for load and store word, we need to find the memory location, right? That's why our desired action is addition. For branch equal to, branch not equal to, our desired action is subtraction. For addition, we do add, subtract, and we have AND operation, OR operation. And set less than, we can have a separate set less than operation. So they have, we have the function field. So the function field determines which of these operations we are going to do. The ALU is going to do which of these operations, and they get this 4-bit ALU value based on what operation you are doing. So you don't have to memorize these. Just understand that for load and store, you need to do an addition with the offset and RS. And they come out with effective ways to, if you have a function value, what should be the 4-bit ALU input. And you don't have to understand this, just understand that this is how they optimized it. And you see these X's, these mean don't care. What don't care means that it can be 0, it can be 1, doesn't matter, whatever it is. So in K-maps, we learned K-maps, right? But in K-maps, we didn't look at the don't care option. So what the don't care option is, it's like this. Like you have 1, 1, 1, X, right? So if it's a don't care here, it will be more beneficial for me to consider that X as a 1, right? So you consider that as a 1. But in this scenario, if there's an X here, it will be more beneficial for me to consider that X as a 0. So that's what don't care is, right? We haven't done don't care in K-maps, but now you know how to do it. But I'm not going to give don't care in exams, but just it's something you should know. Okay. And then using the functions, they found optimized ways to find what should be the 4-bit ALU signals. And using it, they can make one logic diagram, and it can be used inside to know which operation should we perform. But these are not like you can't, this is nothing to memorize, just to understand that this is how it works. Okay. So we know how we control the ALU. So you have the opcode, and these 2 bits. These 2 bits are determined by the function value. Two bits because basically we need to do addition or subtraction or add, or like we don't need to do much stuff. But this is the way how they get these values from control. Okay. So now, if we are doing an operation, an R-type operation, we know we are using RD, right? So we set RD to 1. What this will do is use RD here. RS, RT, we have it, ALU, op. So because we are using RD, we are writing back to the register. So register write is 1. We are not branching. We are not doing a memory read. We are not doing a memory to, like, getting a value from memory to register. We are not writing something to the memory. So for R type format, these are the control signals. This basically has what should be the control signals for all of the operations. So if it's an R type operation, only these will be on. And I will put this in the cheat sheet. So you will have an easier time to know, okay, if it's an R type format, you have these control signals are used. If it's a load word or a store word, you have to use these control signals. So basically, for load word, you are putting a value from memory to register. That's why this is 1. You are also putting you're using the ALU to find like the ALU signifies which memory location you're using for both load and store. So this ALU SRC is set to 1. And this will be in the cheat sheet. So when you are thinking which control signals we are using, you will be able to use this values. Now, we have covered control signals and we have covered how the data flows, right? Now we can go back to the beginning of the slide and show you how does these work. If I make it larger and zoom in. Okay, so for addition, we have RS, we have RT, right? This is 5 bits, this is 5 bits. These select 32-bit values, and this is used. So this goes in and we get this result. We don't use the memory, but bypass it and store the result in RD. The instruction, this sign extend, we don't use it, but we just take the first 6-bit and we use that 6-bit to know what's the instruction. It's an R-type instruction. So these bits will be 0 and it will tell the arithmetic logic unit that we have an R-type instruction. Additionally, the 6-bit, the 5-bit function code, the 1, 2, 3, okay, 6-bit function code will tell us that it's a addition, right? So it also goes into the ALU, and using the opcode and the function code, we know that we are going to perform an addition. While we do that, we also have to set this, REG DST, this says whether we are going to use RD or not. So we are going to use RD, and it's not a branch operation, it's not a jump operation. So the next PC is equal to PC plus 4. So that will be done here. Okay. So we just use, this is PC plus 4, and it will go all the way. It will be selected and nothing else will be selected, and PC will be PC plus 4. Oh. Let's see if I can finish it before it. Yeah. Let's do another one, and then I'll leave something for the next class. So for jump, we know we are not using the ALU, but the instruction opcode just tells that the jump control signal should be on which tells us to use this instead of using PC plus 4, we will use the other option, which takes in the 26 bit, right? The 26-bit address, it left shifts it by 2. So now we have by 2. Left shift by 2 and gets a 28. Now it's 28-bit, and we get the top 4 bits. So the top 4 bits from the existing PC and concatenates it. We get the 32-bit value, and because we said that the jump operation has been selected, it will select the jump operation, and PC will be the jump location. Because we have time, let's quickly look at the branching. So for branching, let's keep it for next class. Yeah. But if you haven't gotten back your quiz 1, like quiz 1, quiz 2, I'm going to check. The TAs are going to check on Monday. So you'll get it back Wednesday. But if you want your midterm or quiz 1, you can follow me to the office. I can give it to you. You can come talk to me that you need, and we can go to the office.